Okay, so now we are going to state one of the beautiful applications of Hartog's extension theorem. So the theorem, or the corollary of Hartog's extension theorem, says that every holomorphic function defined in a neighborhood of a polydisc in Cn extends to the whole polydisc. And this is valid just in higher dimension. In n equal to 1, it's not valid because we have functions like 1 over z, which are defined in the boundary, in a neighborhood of the boundary of the disk, but they do not extend to z equal to 0. Anyway, so for simplicity, we will take n equal to 2, and the proof can be simply done for a higher dimension. And I will try to explain the proof in picture. So first we have to see what is the neighborhood of the boundary of the polydisc. So the boundary of the polydisc will be the full one-dimensional disc times the circle, and the circle and its union with circle times the full one-dimensional disk. And it's so we have to consider holomorphic function in its boundary. So in particular, if we consider its boundary, it's a neighborhood, we will find out that our function is defined in the disk times a oops, otra vez, ¿qué pasó? Okay, so it is defined in the complement. So we have a holomorphic function defined in the disk this disk times the complement of one small disk inside the big disk that I had, because my holomorphic function is defined in a neighborhood, and since it's a neighborhood and disk times circle is compact, we will get we can get this let's say this is small disk such that my function is defined and its complement is for free. Okay, so anyway, so I have a function which is defined in this product. So in order to apply the Hartog extension theorem, I will take two small disks here. First, one small disk which is already in this, let's say, in this ring type shape, and the other one intersecting this this white region. So my objective is to extend my holomorphic function to this white region. So now we can apply. Now we have a Hartog's domain. So let's explain that what is the Hartog's domain. So the Hartog's domain is this one. So this full disk times a small disk, it is already this is small disk. This is in one part of my Hartog's domain, and then a neighborhood. This ring, which is a neighborhood of this circle. This circle times this bigger disk. Remember that my function is defined in a neighborhood of the boundary. In particular, it is defined in a neighborhood of this circle times the whole disk that we have here. So at the end of the day, I have formed already my Hartog's domain. So the holomorphic function is defined in this Hartog's domain. So I will have the extension. So this means that I will get the extension to this part. So this means that at the end I was able to extend it to a part of this white region. And since this small disk is compact, so the idea would be that at the end I can feel my I can feel this region by these small disks. and the corresponding bigger disks, and well, so and the corresponding bigger disks, and at the end of the day, I will realize that this white region can be smaller, and each time the extension will go further inside the white region, and I will get the extension. So if you want to have a precise argument, maybe you can say that you can say in this way. Let's define this white disk in this way, that it is the smallest disk. Well, actually, it is the largest disk that the extension cannot happen. And we see that when we fix any uh, white disk like this, then there will be again further extension. Okay,